All right, so this is our next video on Math 1560, Calculus 1 for U of L, Fall 2017. In this video, we're going to look at classifying critical points. So this is, again, material from section 3.3. So in the last video, we saw that the sign of the derivative, the value of the derivative, lets us know whether a function is increasing or decreasing. And so if you think about what our critical points tend to look like, right? Critical points, a lot of them tend to occur at local maxima or local minima. And if you think about what happens at a local max or a local min, well, these are exactly the places where our function switches from increasing to decreasing or vice versa. So once we find those transition points, right, these critical points, we'll be able to figure out exactly what's going on, right? So for a local maximum, right, we say that we've got a local max if f of c is bigger than or equal to f of x for all x in some open interval containing c. Similar definition for a local minimum. And now, I guess if we wanted to be kind of really picky here, you know, there are some weird things that could go on. Like, for example, we could have something like maybe something like this, right? F of x is equal to 1 minus x squared if x is less than 0, and then just 1 if x is bigger than or equal to 0. And then you get, you know, a graph that kind of looks like this. Okay, it's a parabola when x is negative, and then we have a horizontal line when x is bigger than or equal to 0. And so this point here at 0, 1, technically, if we allow for bigger than or equal, that's a local max, right? And actually, in this case, if you were to work out, you could even use the definition, you could work out that, in fact, that's okay. If you calculate the derivative, f prime of 0 is still 0. That is still a critical point, right? So weird things like that could happen. But that's not what a local maximum tends to look like for us, right? A local max, usually, we're looking at something that, you know, goes up, reaches a peak, and then heads back down, right? Or maybe there's a cusp, so maybe it goes up and then it comes back down, and we do something like that, right? So either you've got a point where there's a horizontal tangent, f prime of c equals 0, or you've got a point where there's no tangent at all, and the derivative doesn't exist. In both cases, notice that if we look at what's happening on either side of the critical point, right, to the left of that critical point, our function is increasing. F prime of x is bigger than 0. To the right, our function is decreasing. It's going down. So over here, f prime of x is less than 0. And even at this, you know, this cusp where the derivative doesn't exist, the same thing is true. It's still true that f of x is positive here, or f prime of x is positive here and negative there, right? So it's still the case that the function switches, the derivative switches from positive to negative. The function switches from increasing to decreasing as you pass through that local maximum. And of course, for a local minimum, it's going to be sort of the same story, except it's the other way around, right? We go like this, and so as you pass through that critical point, well, on the way down, your function is decreasing, so the derivative is negative. On the way back up, your function is increasing, so the derivative is positive, right? So once you find your critical points, the places where the derivative is either 0 or undefined, right? Here's your point where f prime is 0. Once you find these points where the derivative is 0 or undefined, you fill in your sign diagram to figure out where the function is increasing or decreasing. And whenever you see a sign change, a switch from either increase to decrease or decrease to increase, you know you found a local extremum. You know you switched from a local max to to a local min, or sorry, you've switched from increasing to decreasing, so you have a local max, or you switch from decreasing to increasing, so you have a local min. Now you might be something like this, where you go from increasing to constant, right? Now this is only going to happen with a piecewise function, something kind of strange, right? You go from increasing to constant. You could do something like that, but we're going to be interested in what are called isolated critical points. So we want to look at the situations where the derivative is 0 at one point, but it's non-zero everywhere else, to kind of rule out this kind of weirdness. We don't want to deal with the weirdness. We want to deal with this kind of much more familiar scenario that shows up most of the time. Okay, so if we take these observations, we can sum them up as a theorem. So we suppose that f has an isolated critical point, and so again, this means that what this means is that f prime of c equals 0, and f prime of x is going to be non-zero for some open interval, say I, containing c. Otherwise, we could have kind of these weird things where the function is constant on one side of the critical point. We don't want to look at those. We don't want to deal with constant functions either. We're interested in these cases where there's just one point where the derivative is 0. I mean, maybe there's another point later on, but there's some space in between where the derivative is non-zero. Okay. So if the derivative switches from positive to negative, right, that means you're switching from increasing to decreasing, and so you're looking at a local max, right? If the derivative switches from negative to positive, then you're looking at a local min. If the derivative has the same sign on both sides of the point, then you have neither a minimum nor a maximum. So this would be the situation where you have, say, a horizontal tangent, but the function is increasing on both sides of the horizontal tangent or decreasing on both sides of the horizontal tangent. So you might run into scenarios like that, where the derivative has the same sign on both sides of the critical point. That's neither a minimum nor a maximum. Okay, so let's do one example to show how we classify critical points. Here's the same function we saw in the last video. So in that last video, we saw that the derivative was given by 4x cubed minus 16x, and we factored that to 4x times x minus 2 times x plus 2. We drew our sign diagram for f prime, and we saw that there were zeros at minus 2, 0, and plus 2, and that the function was, the derivative was positive for values bigger than 2 and for values between minus 2 and 0 and negative elsewhere. And so now we can see what's going on at each of these critical points, right? Here we go from negative to positive, so we go from decreasing to increasing, right? Here we're going from positive to negative, so we're going from increase to decrease. At 2, we're going from negative to positive, so we're going from a decrease to an increase. And so from the sign diagram, we can see that the point minus 2 and f of minus 2 and 2 f of 2 are both local minima, and the point 0 f of 0 is a local maximum. And I suppose the last thing we should do is actually calculate those values, right? So f of 2 is what? 16 minus 16 plus, sorry, 8 times 4, 16 minus 32. 8 times 4 is 32, plus 5. So that's minus 11. That's also f of minus 2. Notice that the function is even, right? It's only even powers, so negative numbers are going to go to the same value. And f of 0, if we wanted that y value, f of 0 is equal to 5. So now not only have we found the critical points, we know what's going on at those critical points. We know that 2 of them are minima. We know that 1 is a maximum. And this lets us kind of get started on graphing this. If we were interested in graphing, we could plot those minimum values at 2 and minus 2. We could put that maximum up there at 0. And now we know that the graph must kind of look something like that, right? There might be some more details to fill in, but we can guess it's going to look something like that. We're dealing with a polynomial function. We know it's going to go off to infinity as x goes to either plus infinity or minus infinity. So we actually have most of the details. The only other thing I might want to do here is figure out where the function itself is equal to 0, find the location of these roots, and go from there. Okay, that's it for this video.